Today we shall complete the proof that the maximum degree of a node in a Fibonacci heap can be upper bounded by log n, where n is the number of nodes in the heap. And for that proof, we will be utilizing results of the lemmas that we proved in the last lecture. One of the lemma that we are going to use is about the degrees of nodes added as children for a node in a Fibonacci heap. If you remember, we proved that if for a node x we add child nodes y1, y2, etc. up to yk, then we proved that among these children the ith child, that is yi, is having degree greater than or equal to I minus 2. So this is a result that will be used for proving the maximum degree. And before we prove the maximum degree, we shall state and prove few more lemmas, and after that we shall see how we can prove that the maximum number of children for a node in a Fibonacci heap can be upper bounded by log n. So the agenda is to see what is the maximum degree of a node in a Fibonacci heap. First, let us see what is golden ratio phi. This is a very non-constant. The value of phi or golden ratio is 1 plus root phi divided by 2, and this is the value. And it is the positive root of the equation x square is equal to x plus 1. If you find two values satisfying this equation, you can see that this is the positive value satisfying this equation. You try to substitute phi is equal to 1.61803 and see that this formula is correct. Now let us see the next lemma. Here we are claiming that for all natural numbers k plus 2th Fibonacci number is greater than or equal to golden ratio to the power k. We can prove this lemma using principle of mathematical induction on k. For the base case, take k as 0. So the formula becomes f0 plus 2, which is nothing but f2. Fibonacci number at f2. If it starts from f0, f1, f2, and you know that f2 from the definition of the Fibonacci sequence is 1. I hope you remember, otherwise you please refer to the Fibonacci heap. Fibonacci sequence, which is 1. And 1 is of course greater than or equal to phi to the power 0. For any phi to the power 0 is 1. So 1 is greater than or equal to 1. So basically for the base case we are proving that f0 plus 2 is greater than or equal to phi to the power k, phi to the power 0. Then look at the hypothesis assumption. For all values of k from 0 to k minus 1, so for all these values for k, we are going to assume that for any I in this set, fi plus 2 is greater than or equal to the golden ratio to the power I. So this is the hypothesis. Now the induction step, we want to prove it for k. from the definition of Fibonacci sequence, we know that what is fk plus 2? By definition of Fibonacci sequence, it is fk plus 1, the sum of the previous two Fibonacci numbers. Now you can apply induction hypothesis for these values. You can easily see that when you apply induction hypothesis, you will get fk greater than or equal to 5 to the power k minus 2 and fk plus 1 greater than or equal to 5 to the power k minus 1. You just substitute and see. When I is substituted as k minus 2, which is in this set, for which the equation is assumed to be true, when I is substituted as k minus 2, you will get fk minus 2 plus 2 is fk greater than or equal to 5 to the power k minus 2. Similarly, when you substitute I as k minus 1, you will get fk plus 1 greater than or equal to 5 to the power k minus 1. So, this is greater than or equal to this and this is greater than or equal to this. Now, you can try to take out 5 to the power k minus 2 as a common factor. So, this becomes 1 plus 5 because 5 to the power k minus 1 multiplied by 5 is 5 to the power 5 to the power k minus 2 multiplied by 5 is this. So, this is the result that we are getting, and we know that from the golden ratio phi square is equal to 5 plus 1. This is what we know, because phi is the positive root of the equation, x square is equal to x plus 1. So, phi square is nothing but 1 plus phi. Now, if you solve it, you can duplicate it as 5 to the power k minus 2 plus 2, which is 5 to the power k. So, we are proving that fk plus 2 is greater than or equal to 5k, which is exactly what we wanted to prove. So, in this lemma 3, we proved that for all natural numbers k plus 2th Fibonacci number is greater than or equal to 5 to the power k, where phi is the golden ratio. Then, before we prove the final result that we need, that is about the maximum degree of a node in a Fibonacci heap, let us look at this lemma. It says, let x be a node in a Fibonacci heap with k as the degree of x. Then we claim that size of x, which is the number of nodes in the subtree rooted at x. I will give you an example to understand what it is greater than or equal to the k plus 2th Fibonacci number. Given this tree, size of x is the number of nodes in the subtree rooted at x. It is 8, 1 plus 3 plus 3 plus 1. Or if you want to find the size of y, what is it? The number of nodes in the tree rooted at y, it is 4. So, I hope the notation size of x is clear to you. It is the number of nodes rooted in the tree rooted at x. So, we are claiming that if you look at any node x in the Fibonacci heap with the degree k, x is having degree k, then the number of nodes in the subtree rooted at x is greater than or equal to the k plus 2th Fibonacci number. Here again, we can apply principle of mathematical induction in a different way. First, we will look at some other facts and we will formulate a claim which we will be proving using the principle of mathematical induction. So, we take sk, s subscript k as the minimum size of any node with the degree k. So, what is it? If you look at a node with the degree k, sk is representing the minimum size of x. What is the size of x? the number of nodes in the tree rooted at x. So in the in the tree rooted at x, when x is having degree k, we say that sk should be the minimum number of nodes in the subtree rooted at x. Okay. So what is S0? S0 means the minimum number of nodes rooted at a node whose degree is 0. Degree 0 means you only have this node and it is 1. The number of nodes rooted at this node is 1 only, because the degree is 0, you don't have any other nodes. So in this case the minimum is 1 and the maximum is also 1. Then what is S1? S1 means the node you are looking at, which is x, is having degree 1. Then what is the minimum size of the node x, that is the minimum number of nodes in the tree rooted at x? So you can see that the minimum is 2, because the degree of the node x is 1, that itself is giving you minimum 2 nodes, and there could be a very large tree hanging over here, so the minimum is 2. And we can generalize the value of sk. What is sk? The minimum number of nodes in the tree rooted at x when x is having degree k. We can see that sk, the value of sk is monotonically increasing, meaning when the value of k gets increased, sk is also getting increased, because k increase means you are increasing the degree, that means you are adding nodes to the tree, so definitely the number of nodes will increase. Now look at this case where x is the node with the degree k and the child nodes are y1, y2, etc., yk. Not that there could be trees hanging at these nodes, but we are not looking at that. Even without that, by using this notation, we will try to get a formula. We can say that sk, that is the minimum number of nodes in the tree rooted at x, that is sk, is greater than or equal to 2 plus. I am counting these two nodes, that is 2. 2 plus, we apply this formula. Now suppose what is the minimum number of nodes in the tree rooted at y2? It should be represented by s subscript degree of y2, right? S subscript degree of y2, y2 dot degree. Similarly here s subscript y3 dot degree, likewise it goes. I am just applying this formula. When k is the degree of y2, y3, etc., yk. So I can write it like this. I hope you are getting me, otherwise please see again and verify that what I am writing is correct. Now I can write this as greater than or equal to 2 plus sigma I over 2 to k s I minus 2, because from the lemma 1 in the previous lecture we proved that the degree of yi is greater than or equal to I minus 2. This is the lemma 1 that we proved. If you are not able to remember the result, please go back and see that we proved that yi dot degree is greater than or equal to I minus 2. So that is what we applied here. Yi dot degree is greater than or equal to I minus 2. So this is the least possible degree, and now from the monotonicity of sk I can say this. Okay, we will be utilizing a claim to have a result about this sequence. The claim will be proved in the next slide, and the claim is that for every natural number k, Sk is greater than or equal to the k plus 2th Fibonacci number. What is Sk? Sk is the minimum number of nodes in the tree rooted at a node whose degree is k. So we are claiming that Sk will be greater than or equal to the k plus 2th Fibonacci number, that is the minimum number of nodes in the tree rooted at a node whose degree is k must be greater than or equal to k plus 2th Fibonacci number. This we have to prove. Now, assuming that this claim is proved, we are done, because see that Sk is assumed to be the minimum number of nodes in the tree rooted at a node whose degree is k. Okay, when the degree of x is k, Sk is the minimum size of x. Okay, so we have size of x is greater than or equal to Sk, that is what we are saying, and from this claim Sk is greater than or equal to Fk plus 2. So from transitivity of greater than or equal to, we have size of x greater than or equal to Sk from the definition of Sk, and now from the claim Sk is greater than or equal to the k plus 2th Fibonacci number. So it follows that the size of x is greater than or equal to Sk, and Sk is greater than or equal to Fk plus 2 from this claim, and so we can conclude that size of x is greater than or equal to the k plus 2th Fibonacci number, and this is what we wanted to prove. Now, before we prove about the maximum degree of a node, it remains us to prove the claim, so that we can utilize this result to prove a result about the maximum degree. So we will be using this equation for Sk for proving the claim. This is what we wanted to prove, and from the previous equation we will prove it by applying mathematical induction on k. Base case is k equal to 0, and we saw that S0 is equal to 1, and 1 can be written as greater than or equal to 1, no doubt, which is nothing but F2. So we are proving that S0 is greater than or equal to F0 plus 2, which is F2. So the base case is done. Now go for the hypothesis, where we assume that this formula Si is greater than or equal to Fi plus 2 for all values of I in this set. Now we need to go for the induction step for k. From the previous slide we have this equation, Sk is greater than or equal to 2 plus sigma I over 2 to k Si minus 2. I just copied this equation. If you want, you can go back and see that this is the equation that we have. Now just expand it. 2 plus, when I becomes 2 it is S0, when I becomes 1 it is I becomes 2 it is S0, when I becomes 3 it is S1, likewise it goes. When I becomes k, it is k minus 2. Now see that from the induction hypothesis, these are the inequalities we have. S 0 is greater than or equal to F2, S1 is greater than or equal to F3, etc. Sk minus 2 is greater than or equal to Fk. This is what we have from the induction hypothesis. So we can utilize this equation in saying that, okay, we can say it is nothing but greater than or equal to 2 plus this quantity. Using this inequality, we are doing it. Now I can write it as this because I know that F0 is 1 and F1 is 1. So what is F0 plus F1? It is 0 plus 1 which is just 1. So I am adding a 1 to it, then I will get it, and that 1 I am taking from here. It is 1 plus this quantity plus 1, and that 1 is taken as f0 plus f1, which is correct. So this is summation I over 0 to k fi. But from the lemma 2 from previous class, we proved that this summation is nothing but the k plus 2th Fibonacci number. This is the result of lemma 2. If you don't remember, please go back and see that this is what we proved in lemma 2. So we have proved this result, and now we have enough data with us to prove that the maximum degree of any node of a Fibonacci heap represented as d of h dot n, where n is the number of nodes in the Fibonacci heap, is log n. Proof. Let x be a node in a Fibonacci heap with n nodes, and let k be the degree of the node x. So x is a node with the degree k in a Fibonacci heap with n number of nodes. Then we can say that because n is the total number of nodes in the heap, size of x must be less than or equal to n, or the total number of nodes must be greater than or equal to, of course, the number of nodes in the tree rooted at x. That is a very trivial case. Now we have n greater than or equal to size x, and from lemma 4 we know size x is greater than or equal to k plus 2th Fibonacci number. By just combining this and this, from the transitivity of greater than or equal to, we can say that n is greater than or equal to the k plus 2th Fibonacci number, because n is greater than or equal to size x and size x is greater than or equal to f k plus 2. This is true. Now from lemma 3, if you recall, today we proved that the k plus 2th Fibonacci number is greater than or equal to the golden ratio to the power k. This is what we did in lemma 3. Now see, we have n greater than or equal to fk plus 2 and fk plus 2 greater than or equal to 5 to the power k. From these two we can write n greater than or equal to 5 to the power k, where k 5 is the golden ratio. Now obtain what is k from this equation, we are getting the result. So the k must be less than or equal to log n to the base 5. If you know logarithm, it is clear. When you apply log both sides, you will get k less than or equal to log n to the base 5. Why we take the floor is because k is a natural number. And not that this is the golden ratio. So we are proving that the what is k? K is the degree of x. So the degree of x for any x must be less than or equal to log n to the base 5. So we proved that the maximum degree of any node in a Fibonacci heap of n, what it says, is log n to the base 5, where 5 is the golden ratio. So today we proved that the maximum degree of any node in a Fibonacci heap is upper bounded by log n, actually log n to the base 5, where 5 is the golden ratio. This completes the proof that the amortized cost of performing the extract min key NOT operation and the delete NOT operation is log n. The amortized cost is obtained as log n modulo the assumption that the maximum degree of any node is log n. And today we proved the result that the maximum degree of any node in a Fibonacci heap is log n. And see that in this proof we have used 4 lemmas, and all these 4 lemmas are about Fibonacci sequence, and that is why the heap is given the name Fibonacci heap. We saw that it is an efficient data structure which lets you do the decrease key operation in order of one time and extract minimum key node and delete a node operations takes log n time. And with this we are finishing our discussion on Fibonacci heaps. Next class we shall discuss about the next data structure, which is about disjoint sets. Thank you.